All right, this is the second day. We're talking about confidence intervals for a proportion. The first part says, what is the four-step process for calculating a confidence interval? What do you need to do in each step? Do you always have to do these four steps? So you're familiar with the state, plan, do, conclude. I actually have an acronym that goes with that, and it's statistics, problems, demand, consistency. So you'll notice SPDC for the acronym with that. So yes, in general, you should always do it. It's there to give you structure and there to score you as many points as possible on the AP exam. And as far as what you need to do in each step, let's break it down. Let's start with the S, state. And in that step, generally you just need to state what the parameters are, like what parameter you want to estimate. So what are you building the confidence interval for? And then other than the parameter you want to estimate, what confidence level are you going to use? So what parameter are you building this confidence interval for, and then what confidence level? And then for the P, the plan step, we're really looking to check conditions in that step. So check the conditions, make sure they're all good, and identify the appropriate inference method, and we'll talk more about that. Basically, you're just going to say, I'm going to make a confidence interval to try to capture P. And as we get further into the curriculum, you'll see some different inference methods. So this will become more important as we get into that. And then the do step, that one's actually pretty straightforward. You just need to do some stats, right? Perform some calculations. If this was the simulation chapter, you would do a simulation. So whatever it takes for you to prove your point, that's where we're actually going to do some stats in this step. And then what do you need to do in the conclude step? And most of you probably know this by now. So you need to interpret your result, and in this case, the interval that you got. We need to interpret that in context. So that's what the conclude step comes down to. You got your answer in the do step. Now let's interpret it in context in our final step here, the conclude step. So state, plan, do, conclude. Yes, please follow that method. You don't have to write the words every time, although I do. But please follow it. It's there to score you as many points as possible, especially when you know the grading rubric is going to be a 4-part grading rubric. All right, now that we know the formula for a confidence interval, of course, I can introduce to you the calculator command. There is a calculator command. It is okay, especially if you consider multiple choice questions, right? Just throw the numbers into your calculator and let it construct that interval for you. So if you hit stat, test, and then the one we're going to be using for this section would be 1 proportion z interval. So all these intervals can be made with your calculator as long as you're using the right inputs. So it's stat, test, 1 proportion z interval. And when you hit stat test, there's all sorts of inference methods in there. Okay, so a couple points I want to mention here. Definitely show your work to ensure that you get at least partial credit for these type of questions. So in the do step, if you can show your work in regards to what numbers you're using for the p-hat, or for the z-star value, or for the standard error. So show your work, but you can also just revert to the calculator command if that's what you're most comfortable with, and get your answer that way. This just shows the grader that you know what the p-hat value is, and you know what the correct z-star value is. One point to mention though here is don't give 2 answers, right? If you get one by hand, and if you get one by calculator, give the one you think is most correct and cross out the other one, because they'll grade the least accurate one. So definitely do not give 2 answers. Give your best answer only. All right, so let's go ahead and try this 4-step process out on the first example here. It says, in her first grade social studies class, Jordan learned that 70% of the Earth's surface was covered in water. She wondered if this was really true and asked her dad for help. To investigate, he tossed an inflatable globe to her 50 times. Being careful to spin the globe each time. When she caught it, he recorded where her right index finger was pointing. In 50 tosses, her finger was pointing to water 33 times. Of course, Jordan apparently is a young statistician, and her dad is going to use some sampling methods to investigate whether the Earth is truly covered in 70% water. So we commend her dad for that. And we are going to construct and interpret a 95% confidence interval for the proportion of Earth's surface that is covered in water. And we're going to use this data that Jordan obtained by tossing the globe around. Just to give you an idea, it would be like this. So if you threw this globe around, spun it, you catch it and see where your index finger is actually touching. Is it on the water or is it actually on land? So what are the key numbers to highlight here? Well, we got 95%. Apparently it's 33 out of 50. For the state step, what do we want to start with? We want to estimate P. So P is a population parameter. And we can't just stop here. We need to give this some context. So what is P actually? P, which is the true proportion of Earth's surface covered in water. So if you look back to the state step, we've got almost everything. So P is the parameter we want to try to estimate. We're going to build an interval for it. Notably, though, we didn't say how confident we want to be. So we want to estimate it with 95% confidence. Another way to say that is we want to build a 95% confidence interval to estimate P, or to try to capture P, in other words. All right, so I think this is good enough. We defined the parameter, gave it some context, and we said how confident we're going to be with our interval. So let's go to the plan step. So the plan is where we meet our conditions. And if you'll remember, there's three conditions. There's randomness, there's independence, and there's normality. So let's mention something about the randomness that went on here. So it's not like they sampled from a population by any means. Really just spun the globe and try to randomly place a finger on it. So we can assume randomness is okay, right? We'll assume randomness from just by tossing or spinning the globe. So we can trust that that's a random process. So there's nothing wrong with the randomness in this procedure. How about normality? Can we assume that the sampling distribution would be normal? And remember, that's the large counts condition. So we're looking n p hat and n1 minus p hat. They both have to be at least 10. So n was 50, and then p hat would be number of successes. So I guess the ones that landed in the water would be 33 out of 50. So 50 times 33 out of 50. What do you know? 33. So 33 successes, that's definitely bigger than or equal to 10. And then let's go the other way. How many failures did we get? So n1 minus p hat. So if it hit water 33 times, it must have hit land 17 out of 50 times, which would be a failure in this case. So we have 17 failures. So both of those numbers are greater than or equal to 10. So the large counts condition is good, which means we can assume normality. So randomness, okay. Normality, okay. Independence in this case, well, it's not like we're sampling from a finite population, right? Just spinning the globe and catching it. So really, each catch of the globe should be independent of the next one, right? So throwing the globe is independent among trials. There's really not much more to say about that. Just like the globe doesn't have any memory, right? So each trial is actually independent when you spin and catch it. So we can just say throwing the globe is independent among trials. So there's no need to state anything about the 10% condition or anything like that because we're not sampling from a finite population. We're just trying to spin the globe and catch it and look at the proportion of water trials, let's say. All right, so the plan step is good. Random's good, normality's good, independence good. At this time I would say, so we're going to construct a 1 proportion z interval for P, which we already said was the true proportion of Earth's surface covered in water. So if we go back to that plan step for just a second, see it says check the conditions and identify the appropriate inference method. So that's really basically the same thing as which calculator command would you use? So I'm going to move my stuff just a little bit so I can squeeze this in. So within the plan step here, we know all conditions are met now. So we'll construct a one proportion or a one prop z interval for p. And that's all you have to say. There's a lot of inference methods we could use, and we'll get to that later on in the year. But this is the one we're going to use for now. And basically, we kind of just are using the same calculator command name right here in this step. So how much work do we need to show then in the do step? Well, p hat in this case, we had 33 water trials out of a total of 50, so that's 0.66. So let's give p hat the z star for 95%. Okay, we found that before. If we look up at the z chart, it's 1.96. So our actual interval, since we have p hat and z star, we could go ahead and start to build this interval. P hat would be 0.66 plus minus the z star times p 1 minus p. So p is 0.66, 1 minus p is 0.34 over n, which is 50. So this right here would definitely suffice as far as work is concerned. Excuse me. You could go ahead and throw this into your calculator and do one prop z int and get the actual interval at this point. I'm going to go ahead and calculate this though. So this is 0.66 plus minus 0.131 if you crunch this right here. So in red, that represents our margin of error. This one I just simplified it a bit. So if I go 0.131 above and 0.131 below this 0.66, and remember the special name for that is our point estimate, right? That's our sample p hat there. That's our point estimate that we build our interval off that. We should be looking at 0.529 all the way up to 0.791 for our interval. And then the conclude step, we were going to do this regardless, but the problem did say to go ahead and interpret this interval too, right? It said construct and interpret the interval. And hopefully by now we're getting pretty good at this. We are 95% confident that the interval from whatever the lower number is to the upper number, so from 0.529 to 0.791, so we are 95% confident that the interval from 0.529 to 0.791 captures the true proportion. And this would almost get us full credit, it just lacks context. So let's go ahead and give that some context. It captures the true proportion of Earth's surface covered by water. One day I will own one of these. Alright, so the next page here, it says, what is the formula for the margin of error for a confidence interval for a proportion? Is this formula on the formula sheet? Well, no, it's actually not, but the formula is this. So that plus minus piece, where does that come from? So margin of error comes from that plus minus piece that we get in our confidence interval. And the formula that we use is actually like this. You take that piece and set that less than or equal to ME. ME is just whatever margin of error level you want to use. So this is the actual formula. Is it on the formula sheet? No, unfortunately not. Where does it come from? Well, if you think back to the one that's actually on the formula sheet, the z star is the critical value times, this is the standard deviation of the statistic, right? In our case, this is standard error for p hat. And the next part here says, how do you choose a value for p hat when solving for the sample size? Okay, so that basically means, what if they don't give you p hat? What should you set it equal to for just like a default setting? So if you're not given p hat, we in general want to use a conservative estimate for things that we have to basically come up with ourselves. So I want you to just take a second and think about, if I want to be conservative for p hat, the answer to that question is, what's the largest value you could get for p hat times 1 minus p hat? So come up with a proportion for p hat. What's the largest this could be? So go ahead and pause it, think about it for a second. You can try a few values of p hat. What's the value of p hat that makes this the largest? All right, so you probably have already got it, but in case you didn't, the largest this can be is 0.25, and that happens when you choose p hat equal to 0.5, 50-50. We're actually going to use this concept in the next example. Just remember, if you're not given a p hat, we want to use the conservative estimate, so the largest value we could get for this would just be 0.5. Or rather, occurs when p hat is 0.5. So the last example here says, suppose that you wanted to estimate p, the true proportion of students at your school who have a tattoo, with 98% confidence and a margin of error of no more than 0.1. How many students should you survey? So this question is involving confidence intervals. You know the confidence level. In fact, you know the margin of error. What we're solving for, or what we want to know, is n, the sample size. So margin of error of no more than 0.1 for a 98% confidence interval. And now we're going to work backwards and solve for n. So let's keep in mind the formula here for margin of error. Z star, standard error for p hat, is less than or equal to ME. So we definitely are not given a sample proportion in this example. It doesn't come out and say, like, hey, 0.27 of the kids at your school, when you did your survey, had tattoos, right? So nobody's done the research yet. We don't know what the sample proportion is from any sample size. So we're not given p hat here, right? No one's done a sample proportion yet. No one's gone out and actually collected any data. So in this case, we have to let p hat just be 0.5, right? We have to use that conservative estimate. So we know p hat's good. We're actually solving for n. What would z star be? Well, we can usually get that with our calculator or with the normal chart, right? So for 98% confidence, we could do inverse norm of 0.99, or if you want to do the other tail, you could look up 0.01, and it's a z-score. That gives us 2.33 for our z star here. So 2.33 is z star. We're going to use 0.5 for p hat. So let's go ahead and set this up. 2.33, 0.5, and then subsequently 0.5 over n, less than or equal to, they gave us the margin of error to be 0.1. And notice they said of no more than 0.1. So 0.1's greater than or equal to this stuff. So at this point, it just requires a little bit of algebra, and we can solve for n. So let's do the easy stuff first here. Let's divide both sides by 2.33. Okay, so the 2.33 is gone over here, and now we're looking at 0.0429 on the other side. Where'd the 0.25 come from? Well, keep in mind, 0.5 times 0.5. We can simplify that on top. That's just 0.25. Okay, so now we just have the square root in our way. So let's go ahead and square both sides. Once we do that, 0.25 over n is less than or equal to 0.0018. Now we can't solve for n while it's on the denominator, so to get it out of the denominator, let's multiply by n on both sides. So if we want to get out of the denominator, let's multiply by n on both sides. That way, it cancels out over here and shows up over here. So here we are, we've got 0.25 is less than or equal to 0.0018n. So last step to solve for n here, divide both sides by 0.0018. And we get n has to be greater than or equal to 138.88. So I want you to handle this with care. If the sample size has to be bigger than or equal to 138.88, then if you go out and survey 138 people exactly, that just won't do, right? And you can't interview 0.88 of a person, so keep in mind, you've always got to round this up. We got to round it up to the nearest whole person. This is our sample size. So in this case, we'd have to use 139 as the sample size. All right, so we've talked about the four-step process. We talked about how to do these intervals on your calculator, and we talked about margin of error. That is all for these notes. I'll see you in class.